Hai, Assalamualaikum warahmatullahi wabarakatuh dan selamat pagi. Saya ucapkan kepada Dr. Izzat serta rakan-rakan yang dikasihi sekalian. So, pada hari ini saya akan present bagi memenuhi tugasan fizik nuklear iaitu STSN 2142. So, saya telah memilih iaitu liquid drop model untuk saya presentkan pada hari ini. Okey, so baiklah. Kita terus ke slide yang pertama untuk presentation pada hari ini. So, slide yang pertama adalah what is liquid drop model. So, the liquid drop model in physics nuclear is a description of atomic nuclei in which the nucleon behave like the molecule in a drop of liquid. So, kalau anda semua tengok pada gambar raja yang telah saya lampirkan, ini adalah image ataupun cara bagaimana kita memahami ayat yang dimasukkan tersebut. Okey, so kita dah faham apa itu what is liquid drop model. Kita ke slide seterusnya. Okey, so kita akan beralih kepada slide yang kedua iaitu the history of liquid drop model. So kita nak tahu juga macam mana boleh berlakunya liquid drop model ini dalam kehidupan seharian kita ataupun bagi dalam nuklear fizik. So, the liquid drop model was first proposed in 1928 by the Russian physician George Gamow, and later expanded on by Niels Bohr, who is suggested by the observation that all nuclei have nearly the same density. So, the individual nucleons are analogous to molecules of a liquid, held together by short-range interaction and surface tension effects. So guys, we can use this simple picture to derive a formula for the estimate total binding energy of a nucleon. We will conclude or include 5 contributions in the next slide. So as you can see here, kamu semua boleh tengok di sebelah kanan slide ini mempunyai dua gambar, iaitu gambar yang pertama adalah George Gamow dan gambar yang kedua adalah Niels Bohr. So itu adalah gambar diorang yang saya jumpai di internet. Okay guys, so this is the slide where I have been mentioned previously about the 5 contribution for derivation of nuclear binding energy. So we have 5 contribution. So the first one is we have remarked that nuclear force shows saturation and individual nucleon interacts only with a few of its nearest neighbor. So this effect gives a binding energy term that is proportional to the number of nucleon. So we can write this term as C1A, where C1 is a experimentally determined constant. Okay guys, so we continue for the contribution number 2. The contribution number 2 is the nucleons on the surface of the nucleus are less tightly bound than those in the interior. Because, why I say so? This is because they have no neighbor outside their surface. So this decrease in the binding energy give a negative energy terms which is proportional to the surface area. As we can know, it is 4 pi r square. This is because r is proportional to a the power of a 1 over 3, which is a is a mass number. This term is proportional to a the power of 2 over 3, which is the mass atom. We write it as a negative C2, as we can see there, and where C2 is another constant. So let's go to proceed contribution number 3. Contribution number 3 is every one of each of the Z, which is we know as a protons, repels every one of the other proton, as we can see, or we write as a Z minus 1. So the total repulsive electric potential energy is proportional to the formula as we can see over there, which is Z kurungan Z minus 1, and inversely proportional to the radius, which is r, and thus to mass number. which is the power of 1 over 3. So this energy term is negative because the nucleons are less tightly bound than they will be without the electrical repulsion. So we can write this correction as negative C3 Z as the formula that I have write it. So guys, let's proceed to the second last of contribution, which is number 4. So number 4 is observation show that nuclei are most tightly bound if N, which is neutron, is close to Z, which is proton, for small a mass number, and N is greater than Z, but not too much greater for larger A. We know A is a mass number. So we need a negative energy term corresponding to the difference as a formula N minus Z. So the best agreement with observed binding energy is obtained if this term is proportional to the formula N minus Z squared over A. And if we use N equal to A minus Z to express this energy in terms of A and Z, and the term is as I have typed in the slide, which is negative C4 A minus 2Z squared over A. So that's the terms. So finally, the contribution number 5. Finally, the nuclear force favor pairing of proton and of neutron. This energy term is positive if both Z, which is proton, and N, which is a neutron, are even. Or we can say it is more binding. Okay, for the other one, the energy terms is more negative, or I mean negative, if both Z and N, which is Z is a number of proton and N is a number of neutron, are odd. Or we can say it is less binding and 0 otherwise for the condition. So the best fit to the data occur with the term that I've typed in the slide, which is plus minus C5A the power of negative 4 over 3 for this term. So guys, this slide is show that the total estimate binding energy is the sum of the 5 terms that we have discussed previously. Okay, so as we can see in the slide, that is the formula of binding energy in terms of liquid drop model. So the constant for C1 until C5 chosen to make this formula best fit. The observed binding energy are C1 for 15.75 and so on. So the constant C1 is the binding energy per nucleon due to the saturated nuclear force. So this energy is 90 mega electron volt per nucleon, about double the total binding energy per nucleon in most nuclei. Besides guys, we also can use this binding energy formula and apply it in the semi-spherical mass formula as we can see in the slide. So hi everyone, do you want to know more further about the liquid drop model? In this slide, we have the conclusion about it, or we have the answer. So we can understand the efficient qualitative on the basis of the liquid drop model of the nucleus. As we can see in the diagram that have been shown in the slide, the process is shown in it, and in terms of an electrical charge liquid drop. These sketches should not be taken too literally, but they may help to develop your intuition about fission. Okay, so guys, a uranium-235 nucleus absorbs a neutron, as you can see in the figure 1 or in the picture A. It is becoming a uranium-236 nucleus with excess energy, as you can see at the picture of B. So after that, this excess energy causes a violent oscillation during which a neck between two lobes develop, and you can see it on picture number 3. So the electrical repulsion of these two loops stretches the neck further, and it is shown in picture D with D. And finally, two smaller fragments are formed that more rapidly apart, and you can see in the picture E. Okay, before I explain further about the picture in this slide, I want to mention that the qualitative picture has been developed into a more quantitative theory to explain why some nuclei undergo fission and the other don't. So this picture in the slide shows a hypothetical potential energy function for two possible fission fragments. If neutron absorption results in an excitation energy greater than the energy barrier height, which the symbol is UB, fission can occur immediately. So, even when there is not quite enough energy to surmount the barrier, fission still can take place by quantum mechanical tunneling. So in principle, many stable heavy nuclei can fission by tunneling, but the probability depends very critically on the height and weight on the barrier. For most nuclei, this process is so unlikely that it is never observed. Okay, before we proceed to the next slide, I want all of you to focus the picture in the slide that shows the graph. So as you can see, at distance r beyond the range of the nuclear force, the potential energy varies approximately as 1/r. So that's the explanation that I want to explain to you guys about the picture in the slide. Okay guys, so this is the last slide about the liquid drop model, which is about the fission reaction. We all know that fission reaction involves chain reaction. So fission of a uranium nucleus, which is triggered by neutron bombardment, and also release other neutron that can trigger more fission, and suggesting the possible of a chain reaction, as we can see in the picture as I show. The chain reaction may be made to proceed slowly and in a controlled manner in a nuclear reactor, or explosively in a bomb. The energy release in a nuclear chain reaction is enormous, far greater than that in any chemical reaction. So, as the end of the last word, I would like to say that fission liberates about 2000 mega electron volt per atom, which is nearly 20 million times as much energy. So guys, that's all for me, and I hope everyone enjoy with my video presentation. Thank you. Bye.